Hi everybody, welcome to another video in Calculus 3. We will cover two sections on this video. The first section is just an introduction. Right, so what we learned in Calculus 3 up to this point. So first we have a parametric function. So we have a vector So pretty much we have the variable t, but we do not consider that as a variable, as dependent and independent variable. So we call t just a parameter, because when we plot this point, we just plot x, y, z. We do not plot the coordinate t, x, y, z, right? We just plot x, y, and z. T is not one of the axes, right? So what we have earlier is a parametric function or parametric. This gives us a curve in R3, right? And then we have a function of two variables, or maybe three, or could be more. So let's say we might have z equal to function of two variables. So in this case, we have two independent variables and one dependent variable. In this chapter, what we study is a vector field. So a vector field, we have two variables x and y, and then we have two. For each one of them, we assign a vector. So it's like the function of two independent variable, and then two dependent variable. Right. So let's go to a proper definition. Let f and g be defined on the region R in R square in R2. Now, the most important in this section is that we have to focus on every little details, especially on the location, the notation. The notation will be half of a problem. If you can identify, if you understand the notation correctly, then you know exactly what we need to do. If we're confused between the notation, that will be a problem. Right. So a vector field in R2 is a function. Now this is the boldface f that assigns each point in R a vector. So we assign a vector in a point into a vector. So this is not a vector value function. This one is the vector field, because we have more than one independent variable, and we have a vector. So a vector field is written as, it is a vector, so this is a boldface, and we have a vector, so we can write like that. So pretty much we have a point, each point we have a vector corresponding to it. So a vector field is continuous and differentiable if each one of them continuous and differentiable. So let's look at some example. If we have the vector field f of xy equal to 0 on x, or we write x with the j component. By the way, so like I mentioned earlier, the notation is extremely important. Here we have the boldface f. That is a vector, because vector has more than one component. Sorry, that. So that's. So that should be the boldface f. It's a vector. Right. Now. And then of course I, j, k, those are boldface. The boldface are vectors. The regular are function or scalar, or just one component. Right. In different book, you might see the vector v written like this, or the boldface v, or we might see a hat, or we might see an arrow on the top. So the notation for vector will be a lot of different notation. Different books we use different notation. What I use here is I will use the boldface letter to denote a vector. And if we have to write it, I will write like the vector field F. I'm going to write like that, which means the boldface. Right. So here's some example. This is a shear field. For each point x and y, it assigns the vector 0 and x. So for example, at this point, whatever the values is, the x values of this point give us a vector. This is positive. So for example, let's look at the first example. Let's say if we have the vector field at 0 and 1. In that case, the corresponding 0, 0 and x, so we have 0 and 0. So that is not a vector, just a point. Now if we want f of, let's say, 1 and 2, the vector corresponding to that is 0 and x, so we have 0 and 1. So at the point 1 and 2, it's bad that it did not have any cone. Let's say the point 1 and 2, x equal to 1, y equal to 2 is here. X equal to 1, y equal to 2. Let's say that is the point 1 and 2. There's a corresponding vector 0 and 1. So you can write a vector like that. So for each point, we will find a vector and then we just plot the vector at that point. So that gives us a vector field. Earlier I said that vector has no location, but on the vector field, the vector is raw with the tail at that point. Right. So this is one example. A shear field, it is kind of a shear motion. One go this direction, the other one go the opposite direction. So this will go up, this one go down. So go opposite direction. Next one is we have the channel flow given by this. The closer it is to the center, the bigger the vector. The one on the side is a little less. And here we have the rotation vector field given by that. Now, let's take a look at the field example. Make a sketch of the vector field for this vector field. All right, just make a field example. Let's evaluate the vector field at the point, say 1 and 2. Let's do that again. 1 and 2, the vector will be 0 and then x squared, which is 1 squared, still 1. So at the point x equal to 1, y equal to 2, that is the vector that pointing up at 1. Vector, the length is 1, pointing up. Right. Now you could see that at 1 and 3, we still have the same vector. So whenever x equal to 1, we have the vector pointing up like that. Next, if we have f of 2 of 0, for instance, according to this, it's going to be 0 and 4. Right? X, the first one 0, the second one is x squared. So at the point 2 and 0, at the point 2 and 0, the vector is 4. So we have that. So every here. Of course, we might want to write the vector, change the scale so that make it smaller, but that's what we have. And then when x equal to -1 squared is still 1, so we still have that vector. Sometimes we have to scale it back so to have a better field for the vector. But that's what we have. Of course, we can plot more points. And then this is even longer. But that's the idea. For each point, there's a vector, and we draw the vector from that point. Right, let's try another one. F of negative x and y. So, let's say if f of 1 and 2 give us negative x and y, so negative 1 and 2. So at the point 1 and 2, the vector is negative 1 and 2. The vector is negative 1 and 2. At the point 1 and 3, the vector is negative 1 and 3. So 1 and 3, negative 1 and 3. Zero and 1, negative 0 and 1, x equal to 0, y equal to 1. And we just have to plot a bunch of points. So this will be better if we have the computer software. That calculator will not graph the vector field. 1 and 0, negative 1 and 0. One and 1, negative 1 and 1. Negative 1 and 0. It will be 1 and 0. Negative 1 and this is the last one we do is 1 and negative 1. So negative 1 and negative 1, we have 1 and negative 1. So of course we have to graph a lot of this in order to see graph here. We just make a few points. Of course won't be able to see anything, but if we graph a lot more, then we kind of see the flow of the graph. But that's the idea. When we have a point, we have a vector at that point. That gives us a vector field, which usually is a flow of things, and this is very important in physics and engineering. You'll see a lot of this. Right, now we have the same thing in three-dimensional space. So if we have three component function, and we have the vector field of in R3. So the thing about vector field is that we might have a function or transformation if it goes from 2 variable into 3. Maybe 2 by 2, or maybe 2 by 3. But the vector field, we have the point is in the same space. So if the point is on XYZ in R3, it will give the vector in R3. If the point is in R2, it will give the vector in R2. So the point and the vector will have to be in the same space. So that's about the thing about vector field. If the vector field in 3 dimensions, each point is in 3 dimensions, will give a vector in 3 dimensions. So that's the thing about vector field. Right. So vector field is continuous and differentiable. And now we just define the special one is the special vector field called the radial vector field. So like this. Later on we might see this in one of the examples. Next, the gradient fields and potential function. We will have the whole section dedicated to this, section 17.3, I believe. So pretty much what we have is a function. So this is a function. The notation is function, not a vector. But when we'll take the gradient of it, it will become a vector. So if we have the vector field equal to the gradient of that function, then we call that the gradient field, and the function is the potential function. Right. Here's an example. Sketch and interpret the gradient field associated to this 200 minus x squared minus y squared. So first we will take the vector field equal to the gradient. The gradient, that notation is the vector of t. So which means the partial derivative of t with respect to x and partial derivative of t with respect to y. So that is the function. So we just have negative 2x and negative 2y. And draw this on the circular plate. That. So let's just plot a few points. How about 1 and 1? By the way, if we're going to graph like this, it will be very crowded. So we scale it back the vectors. Let's scale that into a bit smaller. For example, now let's just, how about 0 and 1? According to this, we have negative 2 times x, which is 0. Negative 2 times 1 will be negative 2. So at the point x equal to 0, y equal to 1, the vector is 0, negative 2. I'm not going to draw that long though. Just want to draw just half the length. And then f of 1 and 0, negative 2 and 0. So at the point 1 and 0, the vector is negative 2 and 0. And then we can do negative 1 to 0, which gives us 2 and 0. And then we just do all the vectors. So if we plot it, the vector likely will be this. How about it takes 3 and 2? Yeah. So look like everything will point into the center. So what does that mean? So the vector field all kind of point into the same thing. For example, if we have the point 4 and 4 put in here, we have the vector that point inside. So we have the vector field point to the center. And so interpretation of that is this is the vector field when the hit. This is the temperature at the point when x equal to 0, y equal to 0, the temperature is 200. And so the temperature at this point is the highest point, and everything will flow into that. Everything will flow into the center. Right. So, I said this is an introduction section. So just go over the basic. So what you need to know is the vector field. It's just like a function. Vector field in R2 associate the point in R2 to a vector in R2. Vector field in R3 associated a point R3 to a vector in R3. So the point and the vector will have the same dimension, and the point will give a vector. Right. Now we go to actually some calculus. Vector field. By calculus I mean the integral. So in this chapter, mostly we study about integrals. Right. So in this section, there will be two important things. First of all, section 17.2 line integrals. So there will be two types of important line integral. Is the scalar version and then the vector field version of it. So there are two forms of line integral. One of them is the scalar form. The other form is the vector form. So there will be two scalar form and the vector form. Right. If you read the book, that will be rather confusing. They throw a lot of formulas at you, even though there's something else too. But I said to focus only on two form of line integral, the scalar form and the vector form. So what is the difference between the two? So I'm actually will just give you the example of a scalar form. We have a function and then ds. So that is the scalar form. The vector form, we have the vector dot product with dr. So those are the two basic forms of line integral. Obviously, this is the vector, the dot product of a vector. So this gives us just a scalar. This is a function, and ds is a function. Right. Now, look at the first form of the line integral, scalar line integral. Suppose the scalar values function f is defined on the smooth curve parameterized by the arc length s. By the way, don't get too hung up on this. There are much better way to evaluate this integral. The line integral of f over c is given by this. Like I said, it's just definition. Don't get too hung up on that. Don't get too hung up on the parameterized by the arc length s. We don't need to. Right. Now, the next one is a lot more important. We explain what do we need to calculate. The line integral in this is the scalar form. So let f be a continuous function on the region on the smooth curve. Then the line integral of f along the curve c is a curve, is given by that. So the calculation we need is going to be this. So whether this is a scalar form or whether this is a vector form, in the integral there will be two parts of it, two important parts. The first one is whether we have the function or whether we have the vector field. If we just have the function, of course that is the scalar version of it. If this is the scalar function, then we have ds. So essentially, what is the interpretation of this? Because we'll have that in a minute. But in terms of calculation, I said two parts. First, the function, and then the second part is the curve. The curve is given by this. So we can find ds is going to be equal to the magnitude of the derivative times dt. So that gives us ds, and then we just have the function in terms of t. Right. And then our three component will be just that, the same thing. So two important things: the function and then the curve. Right. Let's just look at this example. So for this example, we will evaluate this. So obviously the function in this case is xy plus 2z. And the curve, we need to find the curve. So for the line P to Q, how do we parameterize a line segment connecting two points? We did this in probably the first section, the first chapter, right? So we call a line segment AB is parameterized as we go from the initial point plus the vector connecting them, t between 0 and 1. So that is how we parameterize a line segment. So here we have a line segment from P to Q. So we're going to write first parameterize. I will write out the important step here. So two things, like I said, two important things we need to know is the function and the curve. The curve is parameterized, but actually we will with the parameterized curve first. So the first step is parameterize the curve C. Right. So we're given by this vector C is given by the vector value function from the point plus, so we have P plus the vector PQ. T between 0 and 1. The vector PQ, of course, is the final minus initial. Right, so the point P 1 0 0 plus T times the point subtract 0 1 1, that is Q, subtract 1 0 0, that is P. So we have 1 0 0 plus T 0 minus 1. The notation, it could be vector, could be a point, doesn't matter, they are the same thing essentially. So 0 minus 1, 1 minus 0, 1 minus 0. So combine this, we'll have 1 minus T, 0 plus T, and 0 plus T. So the first thing we need is parameterize the curve. Write the curve as a vector value function or parametric form, either way. But from here we can say this is x, this is y, and this is z, right? So we have x. If we want to, we can write x equal to 1 minus t. When we get used to it, we don't need to. Y equal to t and z equal to t. So first, we have to parameterize the curve in parametric form. Next, the function. Is xy plus 2z. So x is 1 minus t, y is t, and z is also t. So we have multiply now t minus t squared plus t minus t squared plus t plus t, 2t. So we have 2t minus t squared. So that is the function. So we need to have the curve and we have the function. For this, we're going to need the function and the vector field. The vector field and the parameterized curve C. Right. Now with that, we can put it back into the formula. For this one, we will do one more step. Find ds. ds equal to the magnitude of derivative of the parameterized curve times dt. So we determine those two things, but then on this one we will find ds that. So anything in the scalar line integral will do that. Right. This is the vector, right? So when we take the derivative of this, give us derivative of x is -1 respect to t. Respect to t is 1. Respect to t is 1. So we just have that. Yeah. If I have more space, then I'll write them a little bit differently. But we just take the derivative of rt I sub t, and we have that. Now the magnitude of this is square root square of the component. So square root of 3 dt. And then we pretty much go back to the formula. The line integral f ds equal to, now we have the function in terms of t, or we can just say it right like this if we want to. The function in terms of t, and then ds is given by that. And then the limit for t go from 0 to 1. Right. Yeah. So bottom line is, yeah, I think the note here I should write the function in terms of t, and then we have the magnitude of the derivative of r dt go from a to b. So we have ds and the function. So we just multiply those two together. Have the integral from 0 to 1. The function in terms of t is 2t minus t squared. The magnitude of derivative of the vector is square root of 3 times dt. So this square root of 3 dt. I will factor out the square root of 3. Go from 0 to 1 to x. That's 2x minus x squared. So that's 2/3. Sorry. 2/3 times square root of 3. So we have 2 square root of 3 over 3. So bottom line is, for every problem, almost every problem in this chapter, when we are given the curve, we have to parameterize. So that is the first step. When we parameterize the curve, we have x, y, or maybe z in terms of t. Always have to do that step. Whether, I said throughout the chapter, yeah, just parameterize the curve, or we later on we parameterize the surface. But first we need the parameterization. So we know x, y, and z in terms of the parameters. So we need that is the first step. And then after that, determine the function and then ds. This is what we need in this case, right? F and ds. Just multiply them together, integrate. That's pretty much it. Next, parameterize the line from Q to P. Right, so first we have the parameterize of the curve. Parameterize the curve C. The form for that is from Q to P, so we go from Q plus the vector connecting them. And when we write like that, t is between 0 and 1. Right, the point Q, 0, 2, and 2. And then subtract P to Q. And when we do this, we'll have 0, just write out first. 0, 2, and 2 plus t times the vector 2 minus 0 is 2, 0 minus 2, and minus 2. So that is the vector. So we have parameterization of the curve is 0, so that's 2t, 2 plus negative 2t, and 2 minus 2t. T between 0 and 1. So that's the first thing we need is parameterize the curve. We need to know what is x, what's y, and what is z. Don't really need to put this in the equation directly, but here it's nice to know that x is 2t, y is 2 minus 2t, and z is 2 minus 2t. Right. Right. So Q, let's QP from Q and then go to QP. Right. Just test them easily. When t equal to 0, we have the point 0, 2, and 2. When t equal to 1, we have 2, 0, and 0. That makes sense. From 0 to 1. Right. Next we have the function. With that, the function is what? xy plus 2z. That is the function. Right. X, Y. X times Y, sorry. X, Y. Plus 2z. 2 times z. Right, multiply it out. 4t minus 4t squared plus 4 minus 4t. Right, 2t and 2 minus 2t, and then 2z. 4t minus 4t squared plus 4 minus 4t. So the function is equal to 4 minus 4t squared. So next, in this case, we will do f ds, the line integral, the scalar version of it. So that means we're going to compute ds. ds is equal to magnitude of derivative of t dt. So this is r of t. We take derivative with respect to t. 2, negative 2, negative 2. And so I have 2 square plus negative 2 square plus negative 2 square dt. And that gives us square root of 12. Square root of 12 is 2 square root of 3. And finally, the line integral. We're going to write the function in terms of t, which is this. And then ds is equal to that. And we're going to have this as ds, substitute into this. And t is going from 0 to 1. Right, so it's easy enough. We have integral from 0 to 1, the function. So just write the function in terms of t, and then compute ds, square root of 12 dt. Factor out the 12. Yeah, I can just integrate the inside part. So I have 4 minus 4x squared. Yep, going from 0 to 1. So that will be 8 over 3. So I have 8 square root of 12 over 3. Yeah, square root of 12 is 2 square root of 3. Or we can say it equal to 8 square root of 12 is 2 square root of 3. Or 16 square root of 3 over 3. Right, simple enough. So as always, most of the problem in this chapter we have to parameterize the curve or parameterize the surface. Once we have that, this is a scalar form, so we're going to write the function in terms of the parameters. Could be more than one. And then we write the ds. In this case, is the magnitude of the derivative. Multiply those two, the limits, just evaluate. So that's pretty much. That's simple enough. Right, next. Suppose that we have an eagle soar in the ascending path, so it's going to spiral up. So in this case, we don't have to parameterize it. We already have. So parameterize. See, we already have equal to 2400 cosine of, I'm going to write 1/2 t is that, and then 2400 sine of 1/2 t and then 500t. Right, we already have that, and we already have the limits as well. Next, we just need the function, and then we have ds. So what is the function? Well, I didn't say anything about the function, so we assume that it is 1. So this one, just find the length. So in this case, we just let f equal to 1, because it's not mentioned. And we, let's see, how far. So pretty much we ask for the distance travel. And now we find ds. Derivative of r times dt. So we'll take derivative of this. Derivative of cosine is negative sine. So at 2400, negative sine of 1/2 t. And then we have to take derivative of inside. So that chain rule we have to multiply by 1/2. Then 2400 sine of 1/2 t multiplied by 1/2. And then derivative of that 500. Oh, don't forget there's dt. Right, so 1/2, that cancel, we have 1200 sine of 1/2 t, and then 1200 sine of 1/2 t, and then 500. So that is the vector of derivative. If we want the magnitude, we have that sine of 1/2 t don't worry, this will not take as much space as it looks right now. And that 1200. So derivative of sine is cosine. And then 500 square dt. Like negative square, so we just have 1200 square sine square plus 1200 square cosine square and 500 square. Right. The triangle square are common factors. We have sine plus cosine square. Sine square plus cosine square is 1. So we just have 1200 square plus 500 square and the square root. That should be 1300. It is. So we found ds, and we find the function. Finally, the integral f times ds. There's no dot or nothing in between, just multiply, regular multiply. We're going to write the function in terms of t, and then that will be go on this time from 0 to 10. the function will already have 1. And that dt at the end, I forgot the dt, so we have 1300 dt. Yeah, sorry, I forgot there's a dt at the end of it. Right, so we just have 1300 0 to 10 dt, and the integral of that is 10, so we have 13,000. So 13,000 feet in 10 minutes. Right, so simple enough. Again, for this type of problem, first thing we need to do is parameterize that, so we know which one's x, which one's y, which one's z. So in this case, x, y, and z. So we need to write x, y, z in terms of the parameters. Once we have that, we can find a function in terms of t, in this case just 1, and then we find the s certainly in terms of t. Multiply them, integrate. So that's simple enough. Right, so the interpretation, what does it mean, what we did calculate here? So an application for that is, suppose we have the function is one-dimensional density of the wire. Then the mass is given by this. So this scalar version of the integral, what we actually calculate is the mass. So the scalar function, calculate ds, and that'll be it. Right. Number 2, line integral of a vector field. So this is the second part of the section that I want to focus on. So this is the vector form. So the difference is, like I said, I don't know why the book write like this, but some books they write like this form, and actually the textbook that I used back in the day, they use in this form. So let f be the vector field. So completely different than what we have earlier, right? What we have earlier is let f be a continuous function. So this is the scalar function. This is the vector field. So like I said, notation is extremely important. We have to write it correctly. So a capital boldface F is a vector field, is a continuous on the curve. So we need a curve. And let t be the unit tangent vector at each point C consistent with the orientation. Then the line integral is determined by that. So we take the vector field dot with the unit tangent vector, and we have that. And the same thing we have for 3 dimension. Right. If the curve C is parameterized like that, and the vector field is that, then the line integral is given in this form. Like I said, yes, you can see this as a question, but this form is a lot more common. I mean, I think one like this is a lot more simple to do. But when we evaluate it, it's this. So that is the formula. So compared to, now just write on the card so I can refer back later. So first we have the scalar line integral. We have the integral of f ds, which is the integral of the function in terms of t, and ds is the magnitude of derivative of the parameterization dt go from a to b. So this is the scalar integral. Now we have the vector form, or we just say vector line integral. Once again, I'm going to write, instead of this form I can write that form, it doesn't matter. But instead of f, it's going to be the vector field F. Instead of ds, yes, but we have to write the unit tangent vector T ds. Or we have the vector field F dot with dr on the curve C. Or if we're going to parameterize, we're going to write F in terms of T, then dot the product of R prime T dt. So now you can compare between the scalar version and the vector version. Always, if we have the function, write that in terms of T. If we have the vector field, write that in terms of T. So those are the same. This is the scalar, so we're going to need the magnitude. This is the vector form, so we just need the vector. And then evaluate this from A to B. So this is essentially the summary of the whole section. Pretty much just this. Yes, there's a lot of other tiny things too, but said I want to focus on only these two forms. Right, get back to that in a minute. Right, now where do we go from here to here? I'm trying to prove from first one to the last one. So first we start with C, the vector field dot the unit tangent vector ds. Now let's write each component. What do we have? T is the unit tangent vector, so we're going to take the derivative divided by the magnitude. That gives us the unit tangent vector. And what is ds? Well, we talked about this many times. The magnitude of derivative times dt. Yeah. And then F in terms of T. So that's pretty much it. So when we have this, now just substitute everything we have. First, the vector field have to be in terms of T. Dot T is this. And then ds. That cancel out. And we just end up with that. And now we draw the limit for A to B for T, and we have F or T dot or prime of T dt. So that's essentially what we have here. So pretty simple, right? In this case, we just take the derivative. We do not need to find the magnitude, right? So let's look at the form. Evaluate the line integral on the following path. Now you see the difference, right? On the previous one, we are given the function, or if we just find the length or mass, then we have a function. Yeah, we are given the function. This time we have the vector. That means we're going to need the vector form, right? Regardless, we need to parameterize the curve, the quarter circle from C1 to, from this point to that point. So let's draw a little sketch first, because the first step is always parameterize the curve. We need to know what is x, y in terms of t. And we want the curve a part of the quarter circle from 0, 1 to 1, 0. Zero and 1. Oh. To 1, 0. Interesting. So what is C equal to? So that's what we need to determine. By the way, if we go from this point 0, 1 to 1, 0, it goes clockwise. So how do we parameterize that? So usually, if it is a circle, I need to write that for a circle. It is of radius A. Going counterclockwise. From 1, 0. It's going to be A cosine t and A sine t. T between 0 and 2 pi. So if the circle goes counterclockwise, radius A, go from 1, 0 is that. Now this is completely different. It goes clockwise, and it goes from this point to that point. So there's a lot of things to consider. Right. So we have arc T. First of all, we have to make some change. The radius here is 1. That at least we know, right? So radius equal to 1. So we know that. So in this case, it's going to be cosine and sine for sure. So 1 times cosine and 1 times sine of something. Now, we want this to go counterclockwise. I'm sorry, we want this to go clockwise. So in that case, we have to throw in the negative. So in that case, it will go clockwise. So pretty much opposite to counterclockwise. And even, let's just graph and see what happened. In parametric form. And keep that in radian. Yeah. Right, x equal to cosine of negative t. And y sine of negative t. Right, notice the graph. It certainly goes clockwise. That is good, but it's not at the point we want. So we have to go back like 90 degrees. So if we want to go back, do we plus pi over 2 or we subtract pi over 2? Let's try minus pi over 2 first to see if we have the right point. Minus pi over 2. Nope, that's not the point we want. We want, so let's just plus so this we start from that point here, and if we want to change that, we can go from 0 to only pi over 2 because we only want a quarter of a circle. wait a minute, pi divided by 2, sorry. Yeah, the quarter circle from 0, 1 to 1, 0. Right. So this negative guarantee that it go clockwise, and that plus pi over 2, that start pi over 2. So the reason of that, originally you should say cosine of negative of t minus pi over 2. So in this case, the phase shift, it will start pi over 2. Yes, so negative and negative make it the plus. So that's what we have. Right, so that certainly works. If you want to use this, so we can say x is equal to this and y is equal to that. So this is x and this is y. If we want to simplify it, we certainly can. X equal to cosine, I write this as pi over 2 minus t. Cosine over difference. Cosine of a minus b is cosine a cosine b plus sine a sine b. So we have cosine pi over 2 sine of cosine of t plus sine pi over 2 sine of t. Cosine pi over 2 is 0, sine pi over t pi over 2 is 1. So this just equal to sine t. And then y equal to sine of negative, or just write pi over 2. We don't even need to go that far though. This equal to cosine of t. So why is that? What I use this property is called the cofunction theorem. So in general, I can write, let's say I write secant of pi over 2 minus a is equal to cosecant of a. So secant and cosecant. So those functions are cofunction. Secant and cosecant, tangent, cotangent. So tangent, cotangent. Secant, cosecant, sine, cosine. Once we go from a complementary angle, so in general, a function of something, a trig function of something, a complement of that is equal to a cofunction of that angle. So in that case, sine and cosine are cofunction. It goes from complementary angle to that back to angle, that angle. So bottom line is, to simplify, the parameterization should have been just write sine t, cosine t, where t between 0 and pi over 2. Now instead of type that, why don't we just say sine t and cosine t at the same thing. So the first step is always parameterize the curve. So we know which one is x, which one is y. So in this particular case, x is equal to sine t, y equal to cosine t. That's good, right? So that's the first step. We have to know the parameterization, x and t. We know the limit too, so we integrate. Next, the function. If it is the scalar version of it, we will calculate the function. But this time, we have the vector field. Again, I I need more space for this problem. Right, the vector field, given that f is equal to y minus x and x, y, now we write this in terms of t, y is cosine of t, x is sine of t, and then x sine of t. And then next, what we calculate, we have r of t, now we find derivative. Now dr is r prime dt. This is r of t. We will find the derivative. Derivative of sine is cosine, and derivative of cosine is negative sine dt. And finally, we have the vector field, and we have dr. So the line integral pretty much is just f dot dr. So pretty much we just multiply dot product of those two. Cosine of t negative minus sine t dot cosine of t negative sine t dt. That integral go from 0 to pi over 2. Right, dot product. Cosine times cosine is cosine square. Cosine times sine, that minus sine t cosine t. And then sine times negative sine. Right. And we'll just integrate. Right. Hopefully this is equal to something nice and even. Cosine of t. Oh, this for once that is exactly the variable we want. Minus sine t cosine t. Just be careful. Put extra parentheses if we need to. Cosine of t. Sine of t. Minus sine t square dt. Right. Oh, negative 1/2. That's convenient. By the way, I can integrate this by hand too. It will look a little bit messy. Right, I'm going to do this by hand. First of all, cosine square minus sine square. Actually, that is cosine, the double angle of cosine 2t. and sine times cosine is 1/2 sine of 2t. So it's not that bad. Cosine of 2t integral is sine of 2t multiplied by 1/2, or from 0 to pi over 2. Put pi over 2 here, sine of pi is 0, sine of 0 is 0, so this goes to 0. And integral of negative sine is cosine. And then have to divide by the coefficient of t, so we have 1/2 times 1/2, and that again from 0 to pi over 2. So we have 1/4. Cosine, put pi over 2 in here, that gives us cosine pi. And then subtract, where we put in 0 to that. Cosine pi is 1, negative 1, and cosine of 0 is 1, so minus 1 minus 1 is minus 2, minus 2 over 4 is minus 1/2, and that's exactly what we have. So the integration here is not as important, it's how we set it up. So the first step is always the case, whether we do that scalar version or the vector form of the inline integral. We need to know the parameterization, we need to know what is x, what is y in terms of t. In that case, we can write the vector field in terms of t, or we can write a function in terms of t, if it is the scalar version. And then either we take the derivative, or if for the scalar version, we're going to take the magnitude. The only thing is different between the two is one of them is just derivative, the other one is the magnitude. That's all. Of course, the function and the vector field goes different as well. Right. So that's pretty much the concept. The rest of the section we just do more example. Now this quarter circle go from 1 0 to 0 1, so this is standard. I think I showed you how to do this before. Keep your hand steady. Rotate the paper, never rotate the hand. Just rotate the paper. So we go from the point 1 0 to the point 0 and 1. So that's good though, right? This is counterclockwise, starting from 1 0. So this is standard. RT equal to cosine and sine. Radius is 1, so that's why we put 1 1. So don't have to do anything. Yeah, don't have to go here and then work out. So for x and y, in this case x and y, just that. Go just a quarter of the circle, so first quadrant. Yes, so as always, need to find out the parameterization, meaning that we need to know what is x in terms of t, what is y in terms of t, and then this one is different. So the vector field what is the vector field with the problem? Right, y minus x, comma x. So that is the vector field with the problem. Substitute those two in here. We have sine t minus cosine t, comma x cosine t. So that, and next we just need to find the derivative times dt. So from that, take derivative. Derivative of cosine is negative sine, and derivative of sine is cosine. There's a dt. Right? So we write, in this case, if we want ds, then that will put the magnitude. So if this is the scalar version, that will be magnitude of prime of t. And then the line integral f dot d r. So simple enough. Either we write like that, or we want to, we can always write the vector field in terms of t, and then r prime. Limit here is easy, 0 to pi over 2. So we have sine t minus cosine t, cosine t, dot product with negative sine t, cosine t, dt. Right now we do the dot product. The dot product. Right, this one I have more space, so I write more step. So we have first times first. Plus second times second. And then dt. So which give us sine times negative sine square, negative that plus sine t cosine t, then plus cosine square, dt. Right, let's just evaluate this. So look very similar to the previous one though. But a lot more complicated. Alright, sine square. Negative sine square plus sine we need this parentheses. Nah, it doesn't hurt. Cosine of t. Let's just delete. Extra parentheses, so sine t, cosine t, and then plus cosine square, cosine of t square, dt. So that gives us 1/2. So see anything interesting here? So we have the vector field. Along this path, it is positive. Along the one that go opposite direction is negative. So what we see here is the line integral, the vector form. If we go from one point to another, if we reverse it, the values are going to be reversed. Think about this. An application of this is work, for example. The work done, let's say we have the gravity pulling down. So the vector field of the gravity pulling down. relatively. You try to move this object up. If we have to move that against gravity, then we have to put some work to lift it up. So that costs some work. But if you want to drop it from the top back to the bottom, it doesn't require any work at all. We just release and it dropped. And when it hit the ground, what the work it released is the same as when we lift it up. So that's in terms of work. So whereas compared to the previous example, if we're going to do the mass, so this is the scalar version of it. Let's say if we have this part, assume that it's just one dimension. The mass doesn't matter if we go from here to there or from there. Doesn't matter what the direction is. The mass of an object is unchanged. Doesn't matter the direction. If it is in the vector field, it does matter the direction. One direction is positive. If we reverse it, it will be negative. So in this case, that's exactly what we have. So for the vector field, if we reverse the direction of the curve, we have opposite result. Right, more sample. The parametric segment, the parabolic segment, that from 0 to 2 and 4. So this is the curve going that way. So because we have y equal to x squared already, so this usually is natural. We should let one of them equal to t, the other ones depends on it. So in this case, we let of t equal to t for x, and y is t squared. And then x go from 0 to 2. So t go from 0 to 2. Right. Like I said, always find the parameterization first in the most problem in this chapter. Need to know what is x in terms of t and what is y in terms of t. Later on, we might have more than one parameters, like t and s and something else. But that's what we have here. Next, the vector field. Is equal to y minus x, comma x. Yes, it is. So in terms of t, y is t squared, x is t, comma t. That's the vector field. And next, dr. dr is derivative dt. We have the vector field, now we take derivative. From the parameterization, just take derivative. It's going to be 1 and 2t dt. Right, so parameterize, find either the vector field or the scalar function, and then either we find the vector of derivative or the magnitude of it. But in this case, the vector field dot dr. So the notation is very subtle. We see the vector field, we know that we have to have the line integral in vector form. It goes from 0 to 2. The vector field in terms of t. Derivative and dt, so the whole thing here. Let's do the dot product. Times 1 we have t squared minus t plus 2t squared. Yeah, so that's just a dot product. This times 1 plus t times 2t. 2t squared and t squared, 3t squared. I might just use a calculator here. And I have 6. So simple enough, right? So most of the problem in this chapter is like that. If it is vector form, we have to do the dot product. Next, the interpretation of this, the line integral in the vector form is work. So we have the force move an object along the curve C will give us the work. So the interpretation of the vector form of the line integral give us work, whereas the scalar form of the line integral give us the mass. So in the mass form, this is the density. In work, F is the force. Let's go back to page 127, and then we say that is density. And then go to page 129. F is the force. Right. Let's look at this example. Given the force is given that direction, find the work required to move an object on the tilted ellipse from 0 to 2 pi. So, right, we have the parameterization already, so this is good. We don't have to find it. So always need to have x, y, and z equal to something in terms of the parameter. Now the vector field. The vector field is equal x, y, and z. X, y, and z. This is come from the parameterization, come from here. So in terms of t, 4 cosine t, 4 sine t, and 4 cosine t. So we write the vector field in terms of t. The next step is dr r prime dt. So we have that. We'll take the derivative. Most of the section in this chapter is not as long as the previous chapter, but this one is a little long because we have 2 sections. So just take the derivative of this. Negative 4 sine t. 4 sine t is 4 cosine t. The derivative of 4 cosine t is negative 4 sine t dt. So if we have the parameterization, write the vector field in terms of the parameters, and then write either that, take the derivative times dt, or we have the magnitude. So that's pretty much the whole section. There's a little tiny details here and there, but the focus here, of course, in this section is just this. Yeah. both of them require to have R of t in the calculation, so make sure we know that. So I'll write this in terms of t, and it has to be the dot product. Y has to be a dot product, because this is the vector. A dot product of vectors is a scalar, so we're supposed to turn this into just one number. By the way, go from 0 to 2 pi. Alright, so the vector field might not have enough space here, so let's just write in the next line. The vector field 4 cosine t, 4 sine t, 4 cosine t, dot, is the derivative with this. So first time, the first negative 16 sine t cosine t plus 4, that will be 16 sine t cosine t minus 16 sine t cosine t. The line integral, regardless, it's just a scalar. Cancel out. It is radian, yes. So math number 9, go from 0 to 2 pi. And negative 16 sine t cosine t. Right. Cosine at 0. So the work done is 0. So we move from one point, move up, and then move back to the same place. In that case, that's equal to 0. Right. So up to this point, like I said, most important things in this section are those two. It's not that bad to do it. Almost the same thing. The only thing different is this one is the regular product multiplied by the magnitude. This is the dot product multiplied by just the vector of derivative vector. Right. Next we'll define two more things. Like I said, there's a lot of tiny little things in this section, but the focus here, of course, are those two: scalar version and vector form. Actually, the focus on the chapter is the focus on the vector form a lot more than the scalar line integral. Right. Now, it's just a different way to represent things. Right. Let F be a continuous vector field on D, and let C be a closed smooth curve, and that the circulation is defined like that where T. So that's almost the same, but one tiny thing that is not the same as before. So here we have the line integral. I've just put both of them and then we can compare. Right. Let F be a vector field that is continuous on the smooth oriented curve. This is closed, smooth, oriented. So what is the difference? That one have to be a closed curve, right? So on the circulation, we define that on the closed curve. In fact, the notation might not be this. You will see in different book, they will draw a circle here. Even our textbooks do that, but not in this section for some weird reason. So if the curve is closed, we can just draw that. Or may not be even close. We can always just draw the line to grow. And sometimes you might see, and I won't do that because usually this is too small to see it. But you see a little circle, right? I put the arrow to it. So to zoom out, potentially you can write like this. Integral with a circle, and there's the direction. So this meaning that it is on the closed curve and go counterclockwise. It's proper orientation. So yes, but like I said, there's too much details on it already. So just draw a circle, or if you don't want to, just throw them away. It doesn't matter. Like I said, it can be with or without the circle. Somebody used the circle. Right, let's see be the unit circle with the counterclockwise orientation, so that find the circulation of that. So a circle, unit circle, is a closed curve, and this time we have the field given by that. So let's just calculate. For the unit circle, going counterclockwise, so this is pretty standard, right? Parameterize the curve C. This is the unit circle counterclockwise, so pretty standard. Cosine for x and sine for t, sine for y. One complete revolution, one unit circle, go from 0. You can use theta or t, it doesn't matter. So that's what we need, the parameterization, meaning that we need x in terms of the parameter. And the vector field. X is cosine t, y sine t. Simple enough, right? Next, we need dr, which is derivative times dt. R prime derivative is negative sine t. Derivative of sine is cosine t dt. Right, and then the line integral. I usually prefer to write this form though. The vector field in terms of t, derivative is the dot product dt. T go from 0 to 2 pi. Right. So the vector field in terms of t, that derivative negative sine t cosine t dt. Cosine times negative sine negative sine, cosine, and plus sine, cosine. So that gives us what? Sine, cosine, cancel out. So 0. So what is that? Did that make sense? Now think about this. What we call here is this one is the radial flow field. So go from the bottom going out like this. The circulation go in the tangent vector because they are orthogonal. The dot product is equal to 0. So if the vector field point from the bottom out and we go orthogonal to all of the vector field, then it's going to be 0. So that makes perfect sense, because there's the reason we call this is the circulation, right? We go around, whereas the vector field point from the bottom, from the center out, so they're orthogonal, so that will be equal to 0. So that makes sense. So the circulation, that's the reason we call the circulation, because that just go around. Right, next, the same thing on the unit circle, so the same parameterization. It's cosine sine, right? T between 2 pi, 0 and 2 pi. X equal to cosine t, y equal to sine t. Now, the vector field, we need to write that in terms of t, in terms of the parameters. Y sine t, so negative sine t. X is cosine t. We just need to find the derivative dt. Derivative of cosine is negative sine. Derivative of sine is cosine. Right. Then the line integral in vector form. Term of t dot. Oh, after all of this example, I still forgot. Integral in this example go from 0 to 2 pi. Right. The vector field in terms of t, negative sine t, cosine t, dot derivative negative sine t, cosine t, dt. Right, dot product negative sine times negative sine. That is sine square, right? Plus cosine times cosine. Sine plus cosine is 1. So for that, give us just 2 pi. So this is the rotational flow field, so it's flowed, and so the vector field go around, and after parameterization, the circulation, we also go around it. So that's why there's the values is that. So we did have the circulation by the name of it. It just go around the tangent vector. Now the flux. The flux, let that be the continuous vector field defined on that. So almost all of this are the same. This is not on the closed curve though, but the difference here is instead of dot with the tangent vector, this is dot with the normal vector that pointing outward, and n is equal to t cross k. So that seems like a lot of work, but actually it does not. If we write like this, like I said, this is not one of the focus here, so I just have one example and we just do it, and that's it. So we write the vector field and reverse, and we just want to write like that. So in this case we write use x and y, which is fine. Right, next, find our flux across the unit circle with the counterclockwise orientation. So again, unit circle counterclockwise, so that's standard parameterization. And then the vector field is that. This is the vector field that rotational flow, so it flow around. So first, parameterize the curve. Right, unit circle counterclockwise, so that's just standard cosine sine. And of course x is cosine t, y sine t. This is not the focus of this section though. And then the vector field. So negative sine t for y and x cosine t. Right. So this is in the form is going to be f. This is G. Right. I said this is not the focus of the section, so I'm just going to write the formula. So I have f times y prime minus G times x prime dt. T go from 0 to 2 pi in this case. F is negative sine t. Y prime, this is y, derivative of sine is cosine. Subtract G cosine t times derivative of x, derivative of cosine is negative sine. All of that dt. So give us negative sine cosine, negative negative, so that plus sine cosine. That cancel, we just have 0. So actually we could do more example of this, but the flux, what's the flux mean? It go toward the center or from the center out, as opposed to a circulation go around. So one go around and one go from the center pointing out. So in this case, once again, because the vector field going around, but we want the vector that point from the center out, they are orthogonal, therefore it is equal to 0. Right, set. This is not the focus of the section. The focus on the section, of course, only two things. The scalar version of the line integral and the vector version of the line integral. Kind of similar thing when we do this. However, the scalar of line integral, there's not much example we can do, because usually that involving the magnitude, because we have to find the magnitudes of the vector. If it happened to be something like 1 plus x squared, this is extremely painful to find the derivative of. I mean, to integrate this. So that's why we usually have a lot more, and in terms of application also, there's a lot more application in the vector version of the line integral. This only the mass or something else. This could be work, and there's a lot of other things like in electronics. Right, so focus on these two things. Notation is extremely important, whether it's a dot product, whether those are vectors. That helps us to determine what kind of problem do we have. Right. There's two different forms of it. But the first thing we start always is to find parameterization. We need to know what is x, what is y, maybe z in terms of the parameters. After that, depends. If we have the vector field, write that in terms of t. If we have the function, write that in terms of t. Same thing. But if this is a function, we're going to find the s, and that's involving the magnitudes of the derivative. If it is in the vector form, we're just going to take the derivative of it and then multiply dt at the end. And then do the dot product, integrate. So the concept, there's not much. Bottom line is just be mindful with the notation. And then with that, you can certainly know which one we deal with when we look at the problem. But other than that, I'm going to stop this section here. And as always, thank you for watching.